All right, so we have been exploring this idea of buffers and actually kind of getting a grasp on some of the math. Let me show you a shortcut in the math. It is actually just called the Henderson-Hasselbalch equation, and it is on your formula sheet if you want to pull your formula sheet out and look at it if you have not already. And essentially what we're going to do is we're going to rearrange this equation. So I'm going to bring my HA over, okay? Actually, what I'm going to do is actually bring my A and HA over by multiplying by the reciprocal, is what I should say. So I'm going to take concentration of HA over the concentration of A minus and put it on the other side of the equation with my Ka value. I'm then going to take the negative log of it, and what I'm going to get is this guy down here. So the negative log of H gives me pH. The negative log of Ka gives me pKa, and because I'm multiplying my logs, I'm going to add, and then I have the log of my conjugate base over my acid, okay? So this is my Henderson-Hasselbalch equation. And these are concentrations, just so we are kind of aware here. This makes our life a little bit easier when we recognize that we are dealing with a buffer system. Now, you do not have to use this, but it can make your life easier. So let's go back and look at one of our buffer systems we just did. And actually, let's look at this one because this one's kind of an easy one to do. So this was our buffer capacity that we checked out in the last video. Okay, so if I was to, let me clear the ink off just to make this page a little bit easier to work with. There we go. If I was to use this, I would say pH equals pKa plus the log of A minus over HA. Okay, so how does this equation work? Well, we're trying to calculate the pH of these buffered solutions. So our pKa is the negative log of our Ka, because P stands just like it always does for pH as well. It's the negative log, and we're just taking the negative log of our Ka value. So in this case, our Ka is 1.8 times 10 to the negative fifth, okay, plus the log of our concentration of these two species, which in this case is 5.0 over 5.0, okay. Well, 5.0 divided by 5.0 is 1, and the log of 1 is 0. So what we end up with is pH equals our pKa, which essentially just means we're taking the negative log of the Ka, and if you go back and look at our calculations we did for these species, that's exactly what we had, and it gives us simply a pH of our 4.74, okay, which is what we had in the first. Okay, so then what happens from there? We have a reaction. We added HCl to this, and it reacted with the sodium acetate. So we started with 5 moles because we had 1 liter of it, and 5 molar. And we ended up with 4.96 of this guy left over because that was who was reacting. This guy was forming, so we ended with 5.04 of this. So if we jump down here and just change our numbers again, because it's 1 liter, we're dividing by 1 liter, and we end up with those same molarities. We end up with 4.96 over 5.04. Now we can basically do that same math all over again, and we're going to get that same basic pH all over again, which was 4.74 because there was very little change. It ends up being 4.74 or 4.737, so it rounds up to 4.74 with proper sig figs. Now, what I want us to recognize is the Henderson-Hasselbalch equation shows us how a buffer maintains pH. It is maintaining pH because of this ratio. As this ratio changes, our pH, which equals the negative log of the Ka plus this ratio, we're going to see that change in our pH value. So the more this ratio changes, the more our pH changes. The more this ratio stays pretty constant, the less our pH changes, okay, because we're not reacting, or we're not changing as much. Because obviously Ka is not changing because temperature is not changing. So again, we go back and look at a buffer. A buffer should be a weak acid with its conjugate base, okay, or a weak base with its conjugate acid. Ideally, we want high concentrations. Try that again. High concentrations of both of these species, and we want the same concentration for both of these species. The reason being is we want this ratio to stay fairly constant. So with keeping these numbers the same, we are able to have very simple math. On top of that, by keeping high values, we have a high buffer capacity. And again, it makes our math very, very easy. So again, do I have to use the Henderson-Hasselbalch equation? In reality, no. But it is a shortcut, and it can make your life easier. And remember, we're trying to watch time here for this AP exam, so the more time we can save, the better. And this is one of those equations that does help us quite a bit. So let's look at using it in terms of actually making a buffer solution. So with that being said, let's say I want to make a buffer whose pH is around 4 for whatever reason. That's what I'm trying to get. That's what that species survives in, or whatever it is that I'm trying to do. Well, again, if I want my concentrations of my conjugate acid my weak acid and my conjugate base, or my weak base and my conjugate acid to be equal and high values, I'm going to end up with a log of 1, so pH equals pKa, and therefore when I take the negative log of my Ka, I should have around 4 as well. So pH, which is 4.00, equals a pKa of 4. Backtrack this to what a log means. It means I should have a exponent around -4. Okay, so let's look at that in terms of a multiple choice problem on the AP exam. Okay, so let's check this guy out. A chemist needs to have a solution that's buffered around 4.30 and can choose from the following acids. So we have a Ka of 1.3 times 10 to the negative third, a 1.3 times 10 to the negative fifth, a 6.4 times 10 to the negative fifth, and a 3.5 times 10 to the negative 8. And of course we have all of their salts as well. Which system is going to give us the best pH range of this 4.3 for our pH? Okay, which one's going to give us that? Well, if I take the negative log of this, yes, I'm going to get around 3, but remember, if I have numbers here, it's actually going to make it a little bit less than 3. So I would expect my pH range for this one to be somewhere between 2 and 3. This guy, because it's a 5, I'm going to expect it to be somewhere between 4 and 5. This guy also, being a 5, is going to be between 4 and 5. And this one, because it's an 8, is going to be somewhere between 7 and 8. Now from there, we have to recognize how these numbers actually correspond with our pH values. The higher this value, the stronger the acid is. Therefore, the more it's going to bring our pH level down, meaning not as close to 5, it's going to be closer to 4, which in reality is what we're looking here. We're looking for 4.3, which is closer to 4 than to 5. So our best answer here is going to be C, because again, this is a weaker acid, which means it's going to produce less hydronium, so it's going to be a little bit higher up on our pH, so it's going to be a little bit closer to our 5. Actually, if you do the math, it ends up being around 4.89, which again, on the multiple choice section, remember, you don't get a calculator, so you need to be thinking through this a little bit more critically than that. With this one, because it has a little bit stronger Ka value, it's going to produce a little bit more hydronium, which means it's going to be further down on the pH scale, so it's going to give us that closer value to 4, which is what we're looking for with a 4.3. And again, if you actually do the math here, we end up with about 4.2 as our pH value, which is roughly about what we're looking for. Okay, so let's kind of keep going. I actually want to take some time and work through some of these actual problems with you. And again, these come from the AP exam. So this is the 2002, sorry, B. Sorry, I saw the B and thought it was a 2002 question, version B. And I believe this is probably question 1 or 2, knowing how the AP exam worked during that time frame. So what I want to do is spend the next video working through this problem and another problem from the AP exam. Thanks, guys.